slightly less or equally or more depressing topic.
In other news, climate control is the biggest, the biggest issue our nation's facing now, that we said.
Yeah, well, and it does look like.
Yeah, but we won't sign the climate control bill for the entire world or whatever.
It's tough, and really that's central to what this chapter is about. It's politics and money and global health, if you will. And the more I think about it, and I don't know if you guys have a chance or not to look at the talk that I gave in Billings, but I've been able, in a lot of cases, to kind of distill things down into some little tripod or set of, three conflicting interests, so money, politics, and health, I guess, are kind of the three things we're discussing here. And so what we are going to do today is look into sort of the cost of pollution, if you will. We're going to actually try to put a dollar value on it. So let me pop into the figures. And this is one of those, I've been teaching this course for, I guess this is the sixth year. The first time I taught it was fall of 2010. And, I'd already written that paper from, 2008. I started thinking about it in 2004. And it was just kind of like, oh, this is kind of curious, head scratcher. We're still in academia, but it's well beyond the bounds of academia now. It's out in the public. It's in the political spheres, and it's fully in the financial spheres. You have some of the world's wealthiest, most influential people now putting money into renewable energy resource. Bill Gates and his pals, yeah. And I don't know if this is going to be one of those kind of Red Queen problems, or the faster you go, the faster you have to run, or if we can buy our way out of climate change or not. But that's kind of the questions that we're grappling with here.
How do you feel about the Clean Power Plan initiative?
Well, I feel like there's always a right way and a wrong way to do things. I think the wrong way to do it would just be to shut down the coal-fired power plants tomorrow and send everybody home. I think that's the wrong way. My colleagues and I do have some technologies for the CCUS, carbon capture, utilization, and sequestration that I think need to be invested in and developed, researched, and then ultimately implemented. Because there are carbon markets. People buy carbon dioxide all the time, and there are uses for it. So I think it's just a matter of reorganizing the economy, reprioritizing our energy technologies, and really, I don't know, call me a socialist, but making sure that everybody gets their fair share, and nobody's left out in the cold, either literally or figuratively. Yeah, I think this whole winner-takes-all strategy that we've been living with for a while, it's just outdated and not where we need to be as a global civilization.
The Clean Power Plan calls for $276 billion going towards coal-fired power plants to implement CCS technologies.
Okay, yeah.
Like they are giving them a choice anymore. By 2030, they're going to drop off 18 or 30 power plants and build so many new ones.
Mm-hmm. Yeah, the meeting I was in on Monday, we kind of came to the conclusion that renewable energy technologists, will be given these coal-fired power plants to do something with. Biomass, this biofilter technology that I've been talking about a little bit. Maybe turn them into solar towers. Just use solar concentrators, and you've already got the stack there. Put turbines in them. The energy densities are less. You don't get as much bang for your buck. But if you combine that with energy efficiency, where each one of us don't require as much electricity, then I think it can be a much smoother transition.
Have you heard of the Stanford Energy Engineering idea that they came up with at the end of last year? they want to build a three-way system utilizing a natural gas turbine, a wind power turbine, and then a coal-fired power plant with CCS technology.
Oh, sure. Oh, mm-hmm.
And then the wind power will...
Sequester the carbon.
Yeah.
Wind sequesters carbon, yeah. I like it, it's a theme of three, I think it could work, yeah. Yeah. I've drawn up similar diagrams with just using thermal energy and pressure, just getting rid of the carbon and building solar engines. So yeah, I like the idea a lot. And a lot of it's not even new technology, it just hasn't found the proper investment. So, okay. No, I think the world's changing pretty quickly, and I think in general in a good way. Well, you have to. I mean, in fact, with all this monkey business going on in Main Hall right now, and I've spoken with several of you personally and privately, I mean, now is not the time to get afraid or shrug your shoulders or roll over. I mean, now is really the time to stand behind your convictions and your studies and your future profession. And I heard some great advice from a gentleman on Monday who said what you really need to do is just put yourself in the future. What do you want the future to look like, and just look backwards to now, and the path to get there becomes pretty clear, rather than like wringing your hands and worrying, what am I going to do? Just put yourself out there. Where are you going to be? What do you have to do right now to get there? There's going to be things in your way that you need to get rid of, and there's also going to be some doors open and you need to walk through.
Makes sense.
Yeah, no, I made a lot of sense to me. I felt extremely lucky to do
I'm just
that.
glad climate change is a thing now.
Yeah, when Al Gore first started talking about it back in the early 2000s, everybody, some people were on board and everybody else was like, yeah.
Right, yeah, Gore. Yeah, well, that's the trouble sometimes. And I feel the same thing with the protesters out there with the coal signs. I think a lot of times it's actually counterproductive. And I heard Al Gore's message. I mean, I got it. I think he was trying to water things down so most people could, the non-scientifically literate could understand it. But then on the other hand, I think you turn it into a political issue and it loses some weight. Okay, so let's get on into the chapter. I have really enjoyed the conversations today, but let's see what we've got here in chapter 13. So we were halfway through a fairly long subsection. It's subsection 13.3, and it's just called the full financial cost of energy use, and that's a mouthful. I think I talked a little bit last time about the Brandenburg quote with the environment is the economy. We're sort of used to extracting resources, refining them, selling them, making money off them. But now I think it's really time to start reinvesting that money into preservation. So this little figure here is just looking at sulfur emissions, I think to a fairly large extent. I don't know all of the science or the numbers behind it, but we have solved or at least addressed this. I've talked to a lot of people at the clean coal conferences that said, we've cleaned up the SOx, we've cleaned up the mercury, we've cleaned up the NOx. You know what? If we've got to clean up the CO2, we'll do it too. It's not going to be cheap, but we'll figure it out. So what they're just showing here, and this is an example of regional and potentially global sulfur dioxide emissions, creating some kind of impact, and the one that's mentioned is crop yield. So if you have this type of pollution, so that ends up being a cost. Now, what kind of cost would it be? Well, it could be that the government, they're showing a picture of British pounds, the government might now have to pay the farmer who didn't have a high yield just to stay in business so that he doesn't go under and his farm doesn't completely fail and crop production doesn't go down. So there's one small example of a financial cost. You could also look at costs of additional transportation. So if you're not able to grow food locally because you have local pollution. You got to ship it in from somewhere else, cut down another forest somewhere else, et cetera, and it kind of snowballs. Okay. And in table 13.3, I'm just going to read this because I don't have my pad with me, so just follow along. Page 519, table 13.3, it says estimates of marginal pollutant damage in the USA in Netherlands. So they've got SOx, they've got NOx, they've got PM 2.5, and that just means particulate matter, the stuff you read about in Beijing, and we experience some of it here in the valley too. Particulate matter of a size that's 2.5 microns or smaller, and then PM10 particulate matter that's 10 microns or smaller. And just by comparison, a hair on your head is about 70 to 100 micrometers. So these things are, tiny little flecks compared to what sort of a human scale would be. Yeah. So what they're saying, these are in pounds rather than dollars, but they're not that different. The scale is about the same. If we're looking at 3,570 pounds per ton. So that means when a ton of SOx is emitted, that's how many pounds it costs in crop losses. And you could also look at it as that's how many crops were not produced. So that was the reduction yield. That farmer would have made that much more money had that particular pollutant not been emitted into the air. Did you need me?
You're gonna need these strong young men when we were after class.
Okay.
It died right inside the gate. So just barely inside the gate, and it's dead. It's blocking everything.
Do you want to just take a break now so we get her done? I mean, we've kind of been yakking for a while. I'd rather do that than block traffic. So yeah, we can take a break. Okay. That's right. Human powered exercise. Okay, so we were just looking at table 13.3 and talking about the marginal cost, so cost and damage for both the U.S. and for the Netherlands. And now they say, I guess, it looks to me that these were actual estimates in the U.S. and then they said if these emissions were to happen in the Netherlands, this would be the costs. Okay. All right, and this is something I am never all that clear about, so I'm just going to read it out loud. On page 520, it says, the reason for the scale of this market failure is probably the enormous magnitude of the external costs, and we know what external costs are now, the downstream costs. The external costs associated with the emissions of CO2 and other greenhouse gases. Yet, as with the effects of SO2 and particulates, a proper economic assessment of pollution abatement requires a valuation of the marginal damage done by the emission of a ton of CO2. It says this is often given the name the social cost of carbon. And I guess even reading it, it's still not 100% clear in my mind what a social, how you distinguish a social cost from a financial cost. Is that something you guys have seen in another class?
It costs, but you gotta assess it differently. You come out with some kind of social cost.
I can see what a health cost would be. Like I breathed in a lot of bad gas and I had to go to the hospital and pay a doctor for a visit.
Maybe the social cost is like aesthetics, like rivers are less because it's hotter.
Maybe, yeah. So you don't. It could be too. You degraded the environment. So you
Years
don't.
ago, you used to be able to go fishing all summer long, and now there's time restrictions when it starts getting hot.
So
It's too stressful on the fish.
okay.
Maybe.
Could be. Let's read on just a little bit further here. It says since the cost is principally related to global warming, the social cost of carbon can equally apply to other greenhouse gases as long as they are appropriately weighted by their direct global warming potentials. This term has been described in box 13.1 and will be revisited later in the chapter. I'm just going to look up social cost of carbon on the internet here really quick. I know. And I warned you, you wouldn't think that economics would be so confusing, but and the fact there's no equations sitting there makes it 10 times more confusing for me. Like, I have to see the numbers.
How they got it, or how they get it.
Yeah, let's see what.
57 billion.
Yeah, 26 million hits. Let's look at Wikipedia and see. Maybe we'll understand it. I do want to understand what this is. Jump to social cost of carbon. Okay. And I want to review what marginal cost is too.
Total cost is just a per unit cost.
Yeah, so the marginal cost. So I want to make, so yeah, so here's the okay, here we go. So if I want to make just a few of something, they're expensive, right? As soon as I start making more, well, you can even take it to making toast in the morning. So if normally you have 4 people in your house and your toaster fits 4 slices of toast and you stick them all 4 in there, you're gonna run the toaster for 5 minutes and you're gonna get 4 pieces of toast. And so each piece of toast consumed 1/4 of that energy. And then here comes the 5th person at the table. Okay, I gotta run the toaster for another 5 minutes, and now you're sort of up in this. So one piece of toast is here, 2, 3, 4, 5. The price just went up on that next piece of toast. They were going down, and now the next one just went up. Okay, now I get what marginal cost is. Now let's look at. See, I told you I had to see the figure before. Think about toast. All right, so the social cost, marginal cost of emitting 1 extra ton at any point in time. But social cost to what, though? To calculate the social cost, the atmospheric resonance time of carbon dioxide. When we get into 102, we're going to read a paper that talks about resonance time of CO2 in the atmosphere, along with the estimates of the impacts of climate change. Okay, impact of the extra ton in the atmospheric impacts. According to economic theory, if social cost of carbon estimates were complete and markets perfect, the carbon tax should be set equal to that. Emission permits would be equal. In reality, they're not perfect and complete. Okay. Well, it sounds like what we were saying before is true. It's the cost to society in general. It could be less fishing, less crops, fewer sunsets enjoyed out on the back deck. So I guess it's kind of all of the above. Okay. In my other courses, I talk a lot of times about the technosphere and the biosphere, and that's kind of what we're looking at right here. This is the biosphere. This is the technosphere. We interact with it. We just pushed a technology through the snow, right? You could think of the snow as the biosphere, and our hydrogen vehicle is, well, sitting right about there in our human systems. Yeah. And so what we see here, and unfortunately the arrows are sort of pointing down. Every one of these things sort of, okay, so that, humans produce emissions, the emissions accumulate in the atmosphere, the atmospheric concentrations make radiation effects worse, the global climate changes, the weather starts to stink, people get flooded in Texas, and then forests blow away. What we need to do, I think, is somehow just take our little arrow, scoot it over here, and figure out how to just sort of be better stewards of the planet in the first place. You know, put our time and resources into restoration rather than exploitation. I do, before we get into this guy, box 13.4 on page 523. I want to look at this very first number, because a lot of times I'm trying to do a project, right? As an engineer, it's going to cost something. You know, my time's going to cost something, the equipment's going to cost something, the analysis is, et cetera, and the externality is not really accounted for. So what they've done in this figure, this table, is tried to actually put a dollar value on a ton of carbon. So what we're looking at here is, they say 30 to 60 pounds per ton of CO2. I want to see what that costs globally. So I'm going to put myself a little spreadsheet together. I'm going to say low, and this is going to be L per CO2. I have a neighbor by the name of Keegan Eisenstadt, who is in fact a international carbon trader. He deals with entities in Europe who follow the Kyoto Protocol, follow some of these climate change agreements, and he will negotiate financially with colleagues in South America who own land and have the right to cut down forests, but he takes money from the Europeans and pays the indigenous populations in South America to not cut them down. So they're very tempted, like, hey, I could, you know, instead of living my humble hunter-gatherer, fisher lifestyle, I could mow this stuff down, become a rich farmer like Bob over there, and everybody's happy. Well, he's like, you know, hold on a second. There's actually money coming out of Europe to allow you to buy your neighbors, you know, agricultural products and continue to live comfortably. Whatever that means to the.
That's a cool idea.
Yeah. And so, and again, to get back to our little tripod, you know, Keegan Eisenstadt is you know, one of the legs on that, you know, in my opinion, you know, highly functioning tripod. Okay, so let's just look and see what this market might look like. I do not do a heck of a lot of finance, but maybe it's about time. Okay, so we're looking at 30 pounds, 60 pounds, and let's just convert that to dollars. Copy, paste. Some dollars. If you guys want to get fancy in here, I think another thing to do, we could take this, and if you haven't done it before, you can come in, do Control-1, and subscript that. Let's make this a little bit bigger so we can see it. Okay, dollars per CO2, dollars, Control-1, subscript. Okay, so let's just do the current.
$1.52 per pound.
Okay, thanks. So this, and let's just say dollars per pound, 1.52.
Yeah.
It's been holding pretty steady for a long time. I remember that's what it used to be in the 90s. Equals that number times that number. Dink, dink. I'm just going to sloppily copy paste it. That's not right, so I'll take that and drag that box up there. Okay. So between Oh, and this is actually per ton though, isn't it? Ton, oops, let's see. Ton. Okay, let's go back to World O meters. Documents, let's go to courses, let's go to 101, and this is going to be chapter 13. Anybody still been tracking their World O meters prediction from summary 3?
To see if it's gonna hit that, what's projected.
Yeah. Healthcare, social media, environment. Okay, we're at 33 billion tons. You know, I think the prediction is that we'll be close. I mean, I think by the end of the year, you know, if you could take that 33, let's just, yeah, 33. I'm gonna divide that by 11 because we've had 11 months equals. So 11 divided. Oops, sorry. 33 divided by. Let's start over. 33 divided by 11 obviously equals 3. Gosh, I think I'm like 10 steps ahead of myself and falling behind. 33 divided by 11 equals, thank you, times 12 equals 30. Okay, so we might, and I think 33 is a little bit of an underestimate, so 33 billion tons is the estimate for the year. I've heard that 2016, you know, if China keeps building coal-fired power plants, we're on par to hit 40 billion tons next year. Hopefully not. But let's just say tons per year. 36 E9, right? So high. And I hope by now, doing the problem sets in 101, you sort of appreciate the value of keeping track of units. So, you know, we just did, you know, dollars per ton. We did tons per year. Now we just get dollars per year. It just falls around. So we're doing dollars per year equals. Oops. I got ahead of myself again, but let me slip.
Well, that's low.
Yeah, exactly, so. Dollars per year equals the load times the tons per year. This one. Wow.
1.28 trillion.
That's a lot of money. That's some cake. Yeah, so, you know, if the numbers that the authors just gave are accurate, and these guys that wrote this book have been thinking about this a heck of a lot longer than I have, you know, you're looking at a, you know, $1.5 to $3 trillion market. But then the question is like, so where does this money come from? Do the utilities now pay? Well, if the utilities are now paying, where do they get their money from? Do they just get it from the consumer? And then where does the consumer get that money from? Again, it ends up kind of being this Red Queen problem, you know, where the faster you try to throw money at it, the sort of poorer everybody gets all of a sudden instead of the wealthier. So it's not claiming to have an answer, but those are the type of global dollars that we're talking about. I think global GDP, something like 90 trillion. so it's, 1 to 3% of global GDP, so. Okay, glad I did that. I hadn't really looked at that number before. Now, the next one says the price may be considered at which someone's willing to pay to buy the emissions credits in a greenhouse gas trading scheme. At the time of writing, they were looking at 12 pounds. So this is, much less. It's only a third of the numbers we're looking at, or 12 euros or 11 pounds, about a third of the low end that we just looked at. So it's a pollution tax or a penalty price. Oh, and then all the way down, they said a 50 pounds per ton, which is near the top of this, would be 2.5 pence per kilowatt hour. Take care, see you. So 2.5 pence per kilowatt hour for electricity, or 1 pence per kilowatt hour for gas. The reason it's higher for electricity is because electricity, there's a lot of extra equipment involved, transmission, et cetera. Gas, you just put the pipe in place and pump it out. So that would be about a 10% hike in your energy bill. And a lot of times that's why you hear the utility companies saying, we can't do it, it's too expensive, no one wants to pay for it, et cetera, et cetera. Okay. I think we all get that. Okay.
Bill Gates says it's the responsibility of the 1% to foot the bill.
Yeah.
They have the ability to.
Yeah, well, they do, yeah. I mean, I guess, in a sense, I mean, I feel like, sure, I could pay a few extra percentage on my bill. And I guess the flip side of that is like, gosh, if I'm paying more, it would sort of cause me to use less. It would force me to become more efficient with it, too.
Turn the light off when you're not in the room.
Yeah.
Be more conscious of it.
Yeah. Okay. And I'm just going to look one more time down here at table 13.5. It says CO2 damage cost for coal-fueled electricity, and the CO2 at 985 grams per kilowatt hour, we're looking at about 4.9 pence per kilowatt hour. So substantially more than the gas, which they mentioned here. This is obviously a significant cost, and as will be described later, is sufficient to affect the choices made about electricity generation technologies. Yeah, for additional 4.9 cents on your electricity bill per kilowatt hour is something. Well, and if you factor in the 1.5 pennies per pence, we're looking at something like closer to 7.5 cents. We're almost double the cost of electricity in Montana. I'll let you read through the rest of that. The next figure shows what happens when you start to put additional costs onto a power plant. So we've already discussed in the previous chapter what the capital costs are, the operation cost, the cost of the fuel. Well, now if you have CO2 disposal, and that could be, say, putting one of these algae aquatech outfits at each coal-fired power plant, or installing some of the biofilter technologies that my colleagues and I have been working on. That could be a disposal. You're never gonna sequester it all. No technology is perfect. So then beyond that, you've got this so-called carbon price. So it's like, hey, if you're gonna keep using your carbon-based technology, this is how much it's gonna cost you. If you switch over to your renewables, then that whole red chunk goes away, and then, you know, additional costs as well, if those penalties were to be in place. Okay, how are we doing on time here? And this is one long section. Okay. So these are emissions. We were just looking at lignite this morning earlier. It's kind of one of the dirtier coals to burn. It's sort of closer to peat, but it's showing, you know, how little carbon there is associated with some of these other renewable energy technologies compared with all the fossil fuels up top. Same thing here, the relative values. One thing to note is that the wind, there's no fuel cost. The brown there is obviously the fuel cost. Nuclear power, pretty low. All right, I'm gonna take a break here. We only got about 10 minutes left, and there are some very important things I still want to cover. So let's take a pause.